Alright, calculus class. It's the last day of school before break. Making a video because I can. Yes, I am alone in a room. I want to talk about arc length. Oh, yes. Okay, how do we find the length of an arc? Well, finding the lengths of polygons is simple. You just add up the lengths of all the sides of the polygon. But if you have a curved region, how are we going to find the length of that curved region? Well, we can have ad hoc methods for finding the length of certain curves, like a circle, but for finding the length of an arbitrary curve, we realize that we maybe don't know what length is, and so we have to split up those lengths into an infinite number of very, very short lengths, and that will in fact be like the definition of length that we'll adopt. Alright, so imagine you have some curve, f from A to B, and the curve, whatever, looks like this. Well, what we're going to do is to partition this interval up into subintervals, you know, x1, x2, x3, etc. And then we'll call B x sub n, and then this is x sub n minus 1. And what we're going to do is exactly what you would think. We go up to these various points, and maybe we call this P0, P1, P2, P3, etc. And the second to last one, Pn minus 1, and we call this one Pn. Well, if I want to know approximately the length of this curve, then it could take the sums of the lengths of all the segments connecting these. And that's going to be pretty good. So dot 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 and then zone. So basically, I define arc length to be the sum from I equals 1 to n of all of these segments. I guess I want to do pi minus 1 to pi, something like that. And I want to take the limit as n goes to infinity. So as the number of partition goes to infinity. Okay, so what are we really doing here? We're taking the limit as n goes to infinity of the sum from I equals 1 to n of a whole bunch of lengths. And what is the length of each one of these segments? Well, we just distance formula it out, right? This is x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared. And so, yeah. Good. Well, what now? Well, this is really the sum from I equals 1 to n of a whole bunch of small changes in x, so let's just call it delta x squared plus delta y squared. Although, sure. If we do our partition right, these are all each equal, but these are not, so maybe I really need to do like this, because the change in the y is always going to be a little bit different, because as the curve changes. And in fact, what I sort of need to do now, let's see if I'm in frame. Well, what I sort of need to do now is do something with these delta y sub i's. And so what I now do is I say, okay, on each interval, I'm talking about the intervals x I minus 1 to x sub I. On the ith subinterval, I'm going to apply the mean value theorem. So apply the mean value theorem to f. And so the picture is something like this. Here's f, here's x sub I minus 1, this is just a single subinterval, and the function looks like, who knows, something like that. And basically what I can say is, alright, there exists a point where the slope of the tangent line equals the slope of the secant line, or if you prefer, a point c sub I representative of the f function on this interval. This is a picture of f. So actually, what's the case is that f prime at c sub I is f of x sub I minus f of x sub I minus 1 over delta x. And so that means, yeah, well, what is this? This is just the change in y on the ith interval, and this is just the change in x on the ith interval. And so f prime of c sub I is what I called delta y sub I over delta x sub I. And so I can represent the change in y on a given subinterval as f prime c sub I times the change in x. And so, okay, yeah. So that means these sort of small changes in the heights of each of these segments, for that I can substitute a particular derivative at a particular moment. And so we get the limit as n goes to infinity of the sum from I equals 1 to n of the square root of, well, yeah, here we have just delta x sub I squared plus, and in place of this I put f prime c sub I delta x sub I. The whole thing is being squared. So I mean, I'm being very theoretical about this, but really we're just adding up a whole bunch of infinitely small little hypotenuses. That's really all that's going on. We're using the mean value theorem to sort of be careful about it, because these might all be the same, but these might all be different. And you can sort of see what's going on here. When I square these, I can just factor them out. And so this becomes the limit as n goes to infinity of the sum from I equals 1 to n, and I just factor out a delta x squared out of both of these and actually just write out of the square root entirely. And so this becomes root 1 plus f prime c sub I quantity squared delta x. And yeah, do I have anything else to say about this? No. This is an integral. And what is this integral? Well, it becomes the integral from a to b of a whole bunch of things that are all of the form 1 plus the derivative of f squared dx. So that's how you find the length of an arc. Cool? Cool. Let's do like 2 problems right now. Do I have the whole board in frame? Almost. Ah, bad video. Okay, good. Good. And all these problems have kind of just been like worked out to like work out. So okay, let's go. Problem number 1. Find the length of the curve y equals x squared minus 1/8 ln x from x equals 1 to x equals 3. Okay. Sure. Let's do it. So, yeah. I haven't done one of these in forever. So here we go. Let's see. I guess first I need to know what the derivative is. So I have this function, f of x equals x squared minus 1/8 ln x. And then the derivative of this function is 2x minus 1/8 times 1 over x. All right, and so basically I just learned that the length of this arc is going to be the integral from 1 to 3 of root 1 plus this derivative squared dx. All right, so now this just becomes a math problem. Can we take the integral from 1 to 3 of the square root of 1 plus, and now I need to square this guy. So here, okay, I'll write it one more time. Minus 1 over 8x squared dx. And I think just you have to just trust that it all works, because it always all works out, man. So this is 1 plus, I get 4x squared minus 4 to 8. No. Let's see. I multiply them and I get 1/4 times 2, so minus 1/2. And then plus 1 over 64x squared. Okay, but if you see what's going on here, it's kind of a trick because this is the integral from 1 to 3 of root. Well, now the 1 minus 1 becomes plus 1/2. So that's 4x squared. Now it's plus 1/2 plus 1 over 64x squared. But now this is basically the exact same perfect square trinomial that I just had, except it's plus instead of minus. And so you just have to recognize that that's a perfect square trinomial. So really this is the integral from 1 to 3 of root 2x plus 1 over 8x squared dx. And so this is the integral from 1 to 3 of just 2x plus 1/8 times 1 over x dx. And okay, I'm running out of like space to actually do this integral, but this is x squared plus yeah. Why am I suddenly doubting myself? No, this is fine. Yeah, so this is x squared plus 1/8 ln x evaluated at 1 and 3. Is that right? Yeah, of course that's right. Differentiating gives you boom boom. Woo! Weird to be alone in a room. So what do we get? We get 9 plus 1/8 ln 3 minus just like 1 because ln 1 is 0. Sort of I'm going to like do this later and find it's all wrong, but I think currently that the answer is 8 plus ln 3 over 8. Really hope that's right. If it's wrong, it's because I did something dumb. Good. Let's do one more. Which of these looks like easier? Actually, maybe that's like enough. Do we need to do more? Maybe we don't need to do more. Good. No, we'll do one more. Well, all right. Find the length of y equals ln secant x from x equals 0 to x equals pi over 4. Okay, let's do it. I guess we just do it, right? I have a function which is ln of secant, but I feel like this problem's been engineered to work out perfectly because the derivative of this is 1 over secant back inside secant x tan x. So yeah, that's just tan. And yeah, so this is the integral from 0 to pi over 4 of root 1 plus tan squared. Haha. Well, what do you know? That's just secant. So this is just the integral from 0 to pi over 4 of secant. And this one I just like know, I guess. Do I just know this one? Yeah, you multiply by secant x over tan. So yeah, this is just ln secant x plus tan x. And that's happening at 0 and pi over 4. So actual answer, let's see, secant pi over 4 is root 2, and that's 1. So that's ln of root 2 plus 1. And if I plug in 0, I get secant 0 is 1 plus 0, ln of 1 is 0, so this is just the answer. Okay, so that's like regular arc length, so to speak. Parametric arc length is basically the same kind of a thing, although I can't quite do it with the exact level of rigor that I would want. Yeah. So good. So suppose I have some parametric curve now. So I have some, yeah. So now it's this, basically it's the same. Do I even want to do this? Yeah, I guess I'll do this. It's the same thing, but now my curve is kind of doing whatever. And now maybe I'm going sort of this way through the curve. And now I have different points. And I want to, but what I'm really doing is I'm partitioning up a t interval. So I want to do this from t equals a to t equals b. And so I take a certain t interval, so here's A and here's B, and I partition it. And then I look at the ith t interval, so this is t sub I minus 1, this is t sub I, and on that interval, what's happening? Well, on any very small interval, I am making some very small change in the value of my curve. So let this point have coordinates like x of t sub I minus 1, comma, y of t sub I minus 1. And then this point down here is like x of t sub I, comma, y of t sub I, where I'm using those as like, yeah. Okay. And so basically, the total arc length is going to equal like the sum of a bunch of things that are all, well, a sum of a bunch of these lengths. So that's going to be x of t sub I minus x of t sub I minus 1, that quantity squared, plus y of t sub I minus y of t sub I minus 1 quantity squared. Hopefully that's in frame. Okay, so like now you probably want to do like a mean value theorem type thing, but it's kind of annoying, so I don't feel like it. And so I'm just not going to. But what you do is you can do this carefully, but what you eventually end up with is a whole bunch of delta x squareds plus delta y squareds. And yeah, it's the thing is that again, these are all kind of slightly different. But what we can now do is just factor out a delta x squared here. And so we get the sum of root. Inside here we get like delta x sub I squared times, this is inside the radical, like 1 plus delta y sub I times delta x sub I squared. Actually, this is kind of stupid. Do I need to do this? No, I think I don't need to do this. I think I just like kind of leave it, right? Maybe I just kind of leave it and sort of say like, what do we really just end up with? It's sort of basically like this is okay. This basically just turns into the integral, which is the square root of this is just dx dt, and this is just dy dt, and integral from a to b. That's really what's going on here. So I'm skipping the mean value theorem details because it's actually a little bit annoying. What's subtle is that you need to find a sample point in the ith subinterval for t, which can simultaneously be used to like represent the change in x and also the change in y, and it's not like totally clear how to do that. So some like advanced techniques are required that I think are not worth getting into. But essentially, the deep idea is that you're adding up an infinite number of things, each of which is just the hypotenuse of a triangle whose one leg is just the infinitesimal change in x, and whose other leg is the infinitesimal change in y, with respect to t, of course. And so that's why you get this like sort of dt. I think that's pretty good. Let's do a problem. And I think the problem that we should do is the asteroid. And so I will now do that, try to, okay. So what is the asteroid? This is a thing that you did hopefully last year in functions. It's a curve with parametric equations x equals a cosine cubed t, y equals a sine cubed t. And okay, what does this look like? Well, it feels sort of vaguely circle-ish. After all, x is kind of cosine, y is kind of sine. And if you sort of try to plot it, you will see that, like, yeah, when t is 0, we'll be, this will be 1 and this will be 0. So we'll be here at like a comma 0 when t is 0. And when t is pi over 2, you'll get 0, comma a. So we get here t equals pi over 2, 0, comma a. And then when you plug in pi, you'll get negative a, 0. So yeah, negative a is 0, t equals pi. And t equals 3 pi over 2. That's 0, and that becomes a negative a. So you get 0, negative a. Alright, so but what does it look like in between? Well, if you did this last year, you probably just remember. But essentially, what you're going to do is you're just going to kind of look generally at what does sine cubed t look like, sort of overall. And so, I don't know, this is my way of doing it. Normal sine, so to speak, looks like this. So that's like sine t. It's not the best picture ever. Okay, but sine cubed t is going to have these same points, but now if you cube a number between 0 and 1, it's going to get like fatter. No, false. If you cube a number between 0 and 1, it's going to get smaller. So this is going to look... And in fact, so yeah. And since sine t is pretty much t when t is near 0, this is going to be like locally cubic here. And so what you get is this kind of emaciated sort of shape, which kind of behaves like a circle, but in fact sort of comes in like a little bit of, and it's like pointy here. Oh, I guess I should like show that it's pointy. By taking derivatives at those points. Did we maybe do this problem? I think we did this problem back at the differentiation unit. Whoa. So you've actually like totally seen this before. Okay, cool. That was all a waste of 3 minutes. I want to do two things now. I want to find both the area inside the asteroid and the arc length of the asteroid. Okay, let's go. Which one is... Oh, I think the area is the hard one and the arc length one is kind of easy. It's something like that. So let's go. Let's go. Area. Well, how do I find the area of this? Well, I'm just going to find the area of one of these quarters and then just multiply by 4. And basically you just draw a little representative rectangle, and essentially the dimensions of that representative rectangle are like y dx. So the like smooth way of doing these problems is just to realize, I just need to add up a bunch of things that are each like y dx. And well, what is dx? I can calculate dx dt. It is, doing it over there, 3a cosine squared t back inside negative sine t. Yeah. True. Okay. And y is that thing. And I want to integrate from sort of t equals 0 to t equals pi over 2. And this came up today in class as well, because I'm moving, because this curve moves, and it's sort of relevant this way, the arrows are going like this, then the dx's are all negative. So I actually need to throw a negative out there, and then I also need to multiply by 4, because there are 4 of these pieces. So this is negative 4 y dx. Okay, what do we actually end up with here? We end up with negative 4, integral from 0 to pi over 2. Y is just the y coordinate, so that's a sine cubed t. This is dx, and so what is dx? Well, it's 3a cosine squared t times negative sine t dt. Alright, so if I do that integral, I will find the area of this thing. And okay, I can take out the 3 and the a and the negative, so I end up with like 12a squared integral from 0 to pi over 2 of like sine to the 4th t cosine squared t dt. And now I'm going to cheat because I don't feel like doing this right now. And in fact, doing this integral is like kind of annoying, but it is something that we're going to practice more of in like January. So for now, just trust me that this integral is pi over 32. So we get 12a squared times pi over 32. It can be shown. In fact, you could try it, I guess. Good luck. It's like possible, but really, really annoying given your current knowledge. So what is that? I can take a 4 out of the top and bottom. So it's 3a squared pi over 8. And so yeah, that's actually the answer. Is it's 3/8 pi a squared is the area inside the asteroid. And I guess seeing as how the area of a circle with radius a is pi a squared, then I guess the takeaway here is that the area inside an asteroid in general is 3/8 of the area inside the corresponding circle. Which maybe means I drew my asteroid a little bit harshly. That looks like less than 3/8. But anyway, there's the math. Okay, good. Last thing, and then we are done. And you all have homework on finding the tangent lines of two parametric curves, finding the area inside parametric curves, finding the volume as parametric curves are rotated about axes, finding the arc length of parametric curves, and also finding arc length of normal curves. The last thing we'll do is we will find the arc length and this one I think is more chill, to find the arc length of the asteroid. And we do it right now. Well, first we need both dx dt and dy dt. So dx dt I already did, I'll just copy it. It's negative 3a cosine squared t sine t. And then dy dt is very similar. Now if I differentiate, I get 3a sine squared t back inside cosine t. And basically what we learned is that when you're finding the arc length, you're adding up a whole bunch of things, which are each just the sort of hypotenuses of right triangles, in which this is like a tiny change in x with respect to t, plus a tiny change in y with respect to t, and dt. And how do I want to take this arc length? Well, I'm going to go from 0 to pi over 2, and then I'm just going to multiply by 4. Alright, so this whole thing is like, yo, can I do the integrals 4 times 0 to pi over 2 of root? I'm squaring this now, so oh boy. So that's like 9a squared cosine to the 4th t sine squared t plus, this is like 9a squared sine to the 4th t cosine squared t dt. But this is actually like not as hard as it looks like, because okay, I can factor out certainly, so I have 0 pi over 2, I can factor out a 3a, so I get 3a, and what else is in this radical? Well, I can also factor out like a cosine squared t and a sine squared t out of each of these, and I'm left with cosine squared t plus sine squared t, which is 1. So, actually, this whole thing just becomes 12a, integral from 0 to pi over 2, of sine cosine. Sine t cosine t dt. And then, okay, finishing this off, I can steal one of these 2's and put it in there, and that makes it 2 sine t cosine t, so that's sine 2t, and then I'll steal one more 2 to make it for like chain rule purposes. So really this becomes 3a, integral from 0 to pi over 2 of like 2 sine 2t dt. And that I know how to anti-differentiate. It's cosine 2t. And it's, no, I guess there's like a negative in there. Yeah. So negative that, evaluated at pi over 2 and 0. Did I do that right? I definitely did. Good. So, what's the answer? It's negative 3a times, well, what is the cosine of pi? It's negative 1, and the cosine of 0 is 1, so minus 1, and so what we get is 6a. Cool. So that means that the arc length, the length around an asteroid, is 6 times the radius of that asteroid. And actually, yeah, so it's like pretty close to a circle, right? Yeah, because in a circle it's 2 pi r, so this is like basically like 6r essentially. So it's just the length around an asteroid is just a tiny bit less than the length around a circle of the same size, and the area inside an asteroid is 3/8 of the area. So that's everything you ever want to know about an asteroid, I suppose. Alright, good. Calculus, have a nice break. Not the greatest video ever, but decent. Goodbye.